Hello everyone, my name is Ahi Joseph, and today, with my group members Kieran Francis and Samuel Peters, we will be presenting on linked list. What is a linked list? A linked list is a linear data structure where each element or node points to the next. You could kind of think of this as like a shopping list, where each new item is, added sequentially. This is the same for linked lists. Now, these nodes contain the data and a pointer to the next node. This is how they are connected. Linked lists are very good for, dynamic memory allocation and inserting or deleting elements. Now let's get to how these things are utilized in practice.
Hello everyone, it's Kieran Francis here and I'm here to explain this code here to you. So at the very beginning we have include IOStream, which is the library for using cin and cout. Then right after that we have using namespace std. This allows you to shorten the code and basically not allow you to use std colon and then you have cin or cout. This which makes your code more congested. Then we have to define our node structure, which is the linked list. So we have structure node, and then inside the structure node, we have int data and node next. So that int data allows you to enter an integer and it stores it as data. And then we have node next, which is the pointer. The pointer is what stores the address to the other node. Moving on, we have this function here to print the linked list. This function traverses a linked list and prints each node's data followed by this arrow here, which is the pointer, until it reaches the end, and then once it reaches the end, you will get the null. This provides a clear visual representation of the linked list structure. And then we have the function to insert a node at the front of the linked list. So we have the void insert at the front of the head int new data. This preps the node here, it prepares the node, and then moving on here, this sets the node data, it calls new data, and this new data is pointed to the head, the current head, and then we have the head equal new node. Moving on here, we have the function to insert a node at the end of the linked list. So let's keep it short. This function adds a new node to the end of the linked list. It creates a new node with the given data pointing to null. If the list is empty, then it becomes the head, otherwise it traverses to the last node and links the new node, ensuring the dynamic growth. Basically, that's what this part of the code does.
Thank you, Kieran. Now we'll go along with the other functions. First up, insert after. The whole purpose of this function is to insert a new node with the new data after the previous node in the list. The parameters are pointed to previous and also the data that we want to put in. Now, first up, we check whether or not the previous node, the specified node that we want to insert after, whether or not it's null. If it's null, then we have to return. We can't place something afterwards if it doesn't exist. Then we go through the process of creating a new node, assigning the data, putting the data that we want to put in, and also assigning its next pointer. We point it to whatever the previous node is pointed to. The reason why we do this is so we want the new node to be between the previous node and whatever follows after. To do this, we need to have our new node pointing to whatever the previous node is pointing to. And then we'll have previous node point to our new node. And that's the whole process. Next up, delete from end. The whole purpose of this function deletes the last node in the linked list. Parameters are pointed to head. Now first up, we check whether or not the list is empty. If the list is empty, then we return. We cannot delete anything if the list is empty. Next up, if there's only one node in the list. If that is the case, we delete the node and we set the head. We delete the head node and we set the head to null. If all of these things are not the case, then we go along to going through the process of finding the last node. We set attempt to head, and we have a loop which iterates through the list until the second to last node reaches. And then after that, we go through the process of deleting the last node and setting its next pointer to null. Next, we have delete from beginning. And the whole purpose of this function is to delete the first node of the list. Parameters are pointed to head. And we have to check again if the list is empty. If the list is empty, then we cannot delete anything. If that is not the case, then we have a temp to store the head, and we have the head update to the point to the second node, and then we delete the old head. Next up, delete from position. The whole purpose of this function is to delete a node at a specified position in the list. Parameters are pointed to head and also the given position. I will check. First off, we have to check if position is valid. If it's less than 1, then it's not valid and return. If the position is the first position, then we save ourselves through the trouble and just delete from beginning. We call in this function. And we go through, if those two things are not the case, then we go through the steps of setting a temporary node. We set temp to head, and then we have a loop which iterates to the position, moving temp forward by one node in each iteration. And we also check if the position is within range. If it's not, then we return. And over here, we go through the process of actually deleting the node. We store the target node delete, and then we have temp next point to the whatever this node is pointing to, and then we delete the node. And lastly, we go through the process of searching function. This function whole purpose is to search for and print the data of the node at a specified position. Parameters are pointed to the head node and the position of the node to search. Now we also check if the list is empty, and we return if that's the case. Then we again have a temp set to head, and we go through the whole process of iterating up to the position, moving temp forward, which each new iteration to the position, and then when we reach that point, we print the data. Yep. Thank you.
Hello everyone, today I'll be presenting on linked list operations in C++. In this presentation, we will explore basic linked list operations and how they can be applied in real-life scenarios. What is a linked list, you may ask? A linked list is a linear data structure, but unlike arrays, elements are not stored at contiguous memory locations. Each element in a linked list is called a node, and each node contains two parts, the data and reference, or a pointer to the next node in the sequence. There are different types of linked lists, such as singly linked lists, doubly linked lists, and circular linked lists. The code we are working on today is an example of a linked list operation in C++. It demonstrates how we can perform common operations like inserting nodes at different positions, deleting nodes, and traversing the list. These operations are crucial for working with dynamic data structures like linked lists. In C++, a linked list node is typically defined using a structure. As you can see in the code example, each node has an integer data field and a pointer next that points to the next node in the list. This simple structure allows us to dynamically build linked lists of any size, linking nodes together one by one. Here, we are creating three nodes: second, head, and third. The head node holds the value 1 and points to the second node. The second node holds the value 2 and points to the third node, which holds the value 3 and points to null, indicating the end of the list. This is how nodes are linked together to form a chain. Now let's take a look at how we can insert nodes at the front of the linked list. The function insert at the front inserts a new node at the beginning. In this example, we first insert the value -1, then value -3, each time updating the head of the list to point to the newly added node. Inserting a node at the end of the list is also common. Add function insert at the end traverses the list until it reaches to the last node, then appends the new node with the value 4 at the end. This ensures that the new node becomes the last element in the list. Sometimes we want to insert a node after a specific node in the list. The function insert after takes a reference to the second node and inserts a new node with the value -2 immediately after it. This type of insertion can be useful when dealing with lists that needs to maintain a certain order. Deleting nodes is equally important for managing memory and maintaining the list. The function delete from end removes the last node in the list, and delete from position removes a node at a specific position. In this case, position 3. These operations allow us to manage the size of the list dynamically. Once we have nodes in the list, we often need to print the content or search for a specific value. The print list function traverses the entire list, printing each node's data. Similarly, the search node function looks for a specific value. In this case, the value 2, and return to the node containing the value if it's found. Now, let's talk about how linked lists are applied in real-life scenarios. In a music playlist, each song can be a node, and the playlist can be linked where each song points to the next. Text editors use a linked list structure for their undo, redo functionality, allowing users to traverse back and forth between changes. Image viewers use linked lists to provide between images where each image points to the next one. In hash tables, when two different keys hash to the same index, linked lists can be used to handle collisions. Memory management in operation systems use linked lists to keep their track of free and memory blocks efficiently. To wrap up, linked lists are a very versatile and efficient data structures for dynamically managing memory. The operation we've discussed, such as insertion, deletion, and traversal, are essential for various practical applications. By understanding how linked lists work, we implement more flexible and adaptive systems. Thank you for your attention. Now, let's get into some real-life applications of linked lists. The first one is task scheduling. Operating systems use linked lists to manage task scheduling, where each process waiting to be executed is repeated as a node in the list. The next one is browser history. A browser's history is often implemented using a doubly linked list for forward and backward navigation. Next is a music player. Songs in a music player are linked to the previous and the next songs.
Thank you, Samuel. To close it off, I'll be showing you what the output will be if we run the code. Please ignore this -3 at the end. This is for the search function. So here we have the -3, which is the data, the pointer, and then we have another data following, and then the pointer, the data, pointer, data, pointer, data, pointer, and then to end it off we got null. Thank you for watching our video.